Let's begin. Welcome back from a long weekend. I guess long. A lot of activities this weekend. Today is the beginning of the last unit in this course. And it is one of my favorite topics to talk about and teach about and think about and discuss. And finally, you will get to learn about the infamous lobster that you've probably seen around the computer center. People wearing shirts with lobsters, coffee mugs with lobsters in them, T-shirts with lobsters. Okay, you'll get one of those one day. This is a very special lobster that our current TA Ainsley built for me last year. I'm going to pass it around, but this is as valuable as my children. Okay, so be very careful with it. It's 3D printed. Okay, you can take a look. But today, I'll promise you, you will learn all about the lobster and why it's part of the numerical methods culture in our department. Okay, so I'm going to pass this around. Take a look at it. Say hi. You know, it's got some googly eyes, and does it have a name, Ainsley? Did we ever name it? Larry? Larry? Larry. Okay, Larry the lobster. This year his name is Larry. Okay. I want to give you an overview of where you started. We've been together for a long time, believe it or not, right? And I want to give you an overview of where you were when we began this journey together and where we are today. And I want you internally to measure what you've learned. The measure of learning is not absolute. It is relative to where you started and where you are right now. So if you remember, at the beginning, we started very easily. We looked at error analysis. That was kind of not part of a unit in the grand scheme of our story. It was just error analysis, talking about errors. And then we spent a considerable amount of time talking about solving algebraic equations. Those were systems of linear equations, a single nonlinear equation, and multiple nonlinear equations. We recognize that everything ends up boiling to systems of linear equations, right? Even the nonlinear ones, we convert them to linear algebraic equations. Then we spent some time talking about curve fitting and data analysis. We had some data points. We did interpolation. And then we studied regression, which is very different than interpolation. And everything led to systems of linear equations, right? Very powerful. That's why we studied algebraic linear equations in the beginning. Then we had this off topic called numerical calculus, which had numerical integration and differentiation, right? I said it didn't fit in any one of those other story units, right? However, it is important for data analysis when you're doing numerical integration, but numerical differentiation will be important to the topic that we are going to discuss today, which is differential equations. So this gives you a general overview of what this course was teaching you. Now, I would like you to mentally try to plot on the y-axis, assign a value to your knowledge, how your knowledge changed, not an absolute value, relatively. The rate of change of your knowledge, that's important because that's what differential equations are about rates of change. So think about the rate of change of your knowledge, and if I were to plot a curve, I would do something like this. Now notice, initially we started slowly, then we started picking up steam with algebraic equations. I challenged you to think differently about things. We learned some Python, then we hit curve fitting. We had a complete overhaul of our understanding of what standard deviation means, what standard errors mean, etc., how to do regression, arbitrary models, all of that. Think about all of those words that you'd learned and understood. Your exam, you did so well on exam 2, so you understood regression really well. So I know you learned a lot. Then look what's going to happen with differential equations. This is where we get into exponential territory. And differential equations is going to bring in everything we've studied so far and put them all together. Okay? They're very, very powerful. And if I were to say something about differential equations, I was thinking about this morning. I've been kind of going through a midlife crisis, you all know, buying guitars and stuff like that, studying music and etc. So I was reading about tuning forks yesterday, and it hit me. Differential equations are like the tuning forks of engineering science. They are so powerful. They are so powerful that they actually stand behind many of our modern technologies. Yeah, you can bring in quantum mechanics, relativity, etc. All of that can be expressed with differential equations. We're going to learn about them today. I know many of you are taking ODEs now in math, etc. Some of you haven't seen that. That's fine. I'm going to give you an engineering intuitive perspective of differential equations. We will learn about ordinary differential equations. For the most part, we'll touch on PDEs by the end, but still, that in its own is quite valuable to give you an intuitive sense of why differential equations are very powerful. The tuning force of engineering science, that should actually be on the par of like when in doubt, print it out. We'll put it on a t-shirt, differential equations, the tuning forks of engineering science. All right. So I will title this chapter Numerical Methods for Ordinary Differential Equations, and I will teach you how to drive before you learn what's inside the engine. You're not technicians, you're engineers, you're engineering scientists. We're going to learn about how solving ODEs works. But first, I want to give you a taste of what ODEs can do for you. So I'll teach you how to solve them in Python, just like we've been doing from the beginning of the semester. We learn how to do it in Python, and then we dig under the hood to understand what's going on behind the scenes. As usual, we start with a bunch of learning objectives. I'm just going to list those. And that helps me kind of fine-tune my aim of what I want to teach you in this unit. So at the end of this chapter, I hope that you'll be able to define a differential equation, identify dependent, independent variables. We've seen this over and over again. They have a different meaning and different perception with differential equations. Coefficients, the right-hand side of a differential equation. Why that's important, distinguish between a partial differential equation called PDE and an ODE, ordinary differential equation, distinguish and classify ordinary differential equations as initial value problems and boundary value problems, right? Those are two important distinctions. Then describe the meaning of terms in an ODE. So you'll look at a forcing term, at a source term that's bringing in contributing to the evolution of the PDE. You'll study about, to the ODE, you study about advection and diffusion processes, how they show up. Order reduction for high order initial value problems. You'll create Python code to solve a single ODE or a system of ODEs using ODE integrate, ODE int. It's a built-in routine. Create Python code to solve a single ODE or system of ODEs using our own routine. So we're going to do the technician approach, just use whatever is in Python, but you're also going to do the scientific approach where you're going to write your own code, because one day you might create one of those routines yourself and package it so that others can use it. Okay? Use explicit and implicit finite difference methods to calculate a numerical solution for ODEs, for initial value problems. We're still only doing initial value problems here, but there is also boundary value problems which are a little bit harder. And we will use the numerical calculus that we learned just last week about finite differences and how we can convert a boundary value problem into, guess what? A system of linear equations. Okay? So they're going to show up again. And then identify when the right-hand side of an ODE is nonlinear, and then convert that into a system of nonlinear equations, which we solve with fsolve like we've done before. And finally, do an implicit method using Newton's method. We'll talk about that by the end of the semester. Okay, so we will start with an activity. I want you to put your group names out, please. Today, I want you to, this is the most group-centric lecture. Okay, I want you to be buzzing. All right, so I will start with a very simple group activity, and I will ask you just very simply whether you know, whether you don't, whether you've looked at the slides from last year or whatever. What is a differential equation? What do you understand when somebody asks, you're on the bus, okay? You say, hey, I'm doing my bachelor's in chemical engineering, and I know all about physics and stuff. And the guy asks you, what is a differential equation? What do you say? What's the differential equation? Talk, come up with an answer. Let's do it. It is an equation, I know. Obviously. All right. Gaussian eliminators, do you have an answer? Couple good points. Go ahead.
Just kind of like I was thinking, it's like you have observable things that happen, right? And the differential equation is going to figure out why those observable things happen. Rowan kind of said, like,
you're relating two things, okay. But how is that different than just a standard formula, like a standard equation, like saying, for example, the population is equal to e to the minus 5x or 5t, right? So how is the differential equation? You're right that it relates two things or many things together. But how does it relate them? Think about the title. Okay. Bernoulli?
Does it relate like
Yes?
the variable and its rate of change?
Its rate of change, okay, so that's where the word differential comes in, right? It relates the rate of change between multiple things, right? That's a differential equation. It relates the rates of change of things to each other. But that's like a very technical definition, right? It's like what a mathematician or a lawyer would answer you, like what's a differential equation? It's an equation that has derivatives in it. So what? Okay, so we'll start there, and then we'll understand why that's very powerful. So indeed, I'll give you that technical definition. It's an equation with terms that involve derivatives or rates of change. So think of derivatives now as rates of change, as how fast something is changing, or how is it changing in space or time. Rate of change. Keep that word in mind, okay? Of some unknown quantity. So here's an example of a differential equation like the one we will study in these lectures. You'll learn that this is a advection diffusion equation. I'll explain that later. But for now, you see that there is derivatives. There's a second derivative in the first term. There's some coefficient. There's the first derivative and the second term, right? And there's another coefficient. So let's just get the nomenclature down. We call this t, the symbol inside the derivative, as your dependent variable. Okay, that's the quantity that you're trying to understand how it's changing. In this case, it is temperature. Okay? Could be pressure, could be density, could be velocity, could be momentum, could be concentration. It's a dependent variable. Why? Because it depends on other things. It depends on space, it depends on time, it depends on speed, it depends on diffusion properties, etc. Now, what is being differentiated with respect to, we call that the independent variable, because that is kind of chosen independently from the dependent variable. You say, I want to study heat transfer in this mug. So you've defined the space over here independently. And then the temperature will be dependent on that space, okay? And then finally, you have a bunch of coefficients. In here, they're like k and u, could be anything. Those coefficients could be a function of the independent variable and the dependent variable. So k could be a function of t and x, and u could be a function of t, or u could just be a function of x, and so on, okay? Many variations. All right, great. So that looks like a differential equation. Now, why do we develop equations with rates of change in them? So that's the technical definition. Yes, a differential equation is an equation that has derivatives in it. But why? Why do we need equations with derivatives? Why can't we just say t equals something? Usually, that's pretty much impossible to say t equals something, but I want to prove that to you, okay? And I'm going to say it's often easier, and that's what we found throughout the years with geniuses, you know, like Newton and Euler and Bernoulli and all of those great people, that it's easier to describe natural laws by finding relations between rates of change rather than the values themselves. So rather than trying to figure out what the temperature is going to be in this mug if it has coffee or tea or hot water in it, we look at the rate of change of the temperature. It turns out that that's easier to describe. it might be a little bit mind-boggling for you, but once I go through the example, you're going to be like, yeah, this kind of makes sense. It is easier to do it that way. All right, so we're going to do an example. I'm going to take you on a huge tangent now. We're going to talk about populations and how they grow. Why? Because they're very kind of easy and intuitive to understand. So we'll do an example with populations. We'll try to derive a formula that is very difficult to derive, and then we'll derive it in a different way using differential equations, and you see that that's going to be much easier. Okay, so I call that motivating example for using differential equations. So that's a tangent. We're going to go on the side, because I feel like it's also my duty to talk a little bit about differential equations and describe what they mean. Okay? You might not get that when you're taking a course on pure differential equations. We're going to prove theorems and existence, all of that. I don't prove that here, right? Because I rely on the math people to do that. But here I want to understand the intuition. Okay, so I want you to consider a unicellular organism such as the paramecium. I learned about that a few years ago. Apparently, this organism, after a certain period of time, it just does cell division. So it splits in half. Those of you who know biology, I'm terrible at biology, but this is cellular division. Please correct me if I'm wrong, but apparently this organism splits in half after a certain period of time, right? It looks like this under the microscope. In this population, the individuals divide once per day. So if you start with 3, the next day you're going to have 6, the next day you're going to have 12, and so on. Okay? And so starting with a population of a single organism, like after a day, you're going to get 2, and then you're going to get 4, and so on and so forth. And you see kind of that rise in the population. Okay? So if you're starting with an initial population, call it P0, could be a single paramecium or 50 or 7. Okay? P0, that's the initial population. After 1 day, we have P1. Right? We're going to call the population P1 for 1 day. That's 2 times P0. Right? That's by definition the population rate. After 2 days, P2, which is P of 2 days, it's 2P1, which is 2 squared P0 or 4P0. So now, I'll ask you, what is the population of paramecium, paramecia, I guess, PT after T days have passed? It's a simple recurrence formula that you can develop. Okay, we're just warming up here, okay? All right, so I hear an answer here, Danner?
It's going to be P0 times 2 to the power of T.
Okay, and how did you derive that? Okay, I agree. Okay, so let's see how they got the answer. So you can do this by observing a pattern. That P1 is 2 to the power 1 P0, P2 is 2 to the power 2 P0, then P3 is 2 to the power 3 P0. And if you know how to prove something by induction, like in recurrence formula, you say, assume it's true for n. So you say P at n, P after n days is 2 to the power n P0, then prove it for n plus 1, right? And indeed, what happens, you get 2 to the power t P0 after t days. Okay. Now, in general, organisms don't divide, just split in half, right? There's a more complicated process. There's, as you go through, more complex organisms, these organisms, they're going to meet each other, they're going to court, they're going to, start making babies, and behold, the lobster, okay? So consider a population of lobsters. These lobsters are chilling on the ocean floor, okay? They meet each other, they get married maybe, they start making babies. Some of them die, some of them are eaten, by people or sharks or other things, right? But in general, that population doesn't grow by a fixed factor like 2. It doesn't multiply by that. It's actually, in general, some growth rate R. And indeed, you follow that same formula. The population of lobsters after T days is that intrinsic growth rate of the population of lobsters, how fast they multiply. The population of rabbits, for example, is a different R. It's probably very high, right? Population of elephants is low, or like pandas, right? So that R number changes based on the population. But the formula still obeys, starting with an initial population of P0. After T days have passed, you have R to the power T, P0. It's like, think of it as compound interest, okay, in your bank account. And more realistically, instead of writing r to the power t, it's still an exponent. We like exponential forms because the exponential has nice properties with derivatives, etc. So we write this, we convert this r to the power t, so we write r as log r, so we get e to the power rt for simplicity, and we call, it's just a simple sleight of hand. You're just changing nomenclature. Instead of capital R, we put this lowercase r just for simplicity. So we're dealing with e to the rt times p0. Okay? And this lowercase r is a kind of compound interest per unit time. Okay? How fast the population is growing. In population lingo, they call this the intrinsic growth rate of a population. And it's a property of a population. Lobsters have an intrinsic, well-known, like, American lobsters have that kind of, have a special value, fixed value of R, and so on. Okay? All right. So now, just to think about this equation intuitively, if R is positive, then that population is growing over time, right? If R is 0, then it's not changing. There's equal birth as there are death in the population or predation. And if R is negative, then the population is collapsing. It's actually going to shrink over time. Okay, good. Now, in reality, this is I have to set up the stage to tell the story, right? Don't forget, we're learning about differential equations. It's not a course on populations, okay? But it's still kind of fascinating thing about populations. Now, in reality, populations are bound by available resources, okay, and other things. But let's say, let's put the resources, food. Let's say there's no predation in this case. There's just food limitations and competition. And after some, limit after some time, the population reaches a maximum capacity. We call that K. Initially, there's like exponential growth. They're all kind of, getting together, etc. They're overpopulating. Some of them start dying. But then there's competition for resources. They cannot grow any further. So they reach a capacity. And that's called a maximum carrying capacity in population lingo. And we call that K. So it probably looks something like this curve over time. Okay? And once the population reaches that K, there's a balance between how many individuals are born, how many are dying, how many are not surviving, and so on. Okay, so now here's the challenge. And this is how I'm going to tie this into differential equation. It was easy for you to derive the equation 2 to the power t p0 or p0 e to the rt. What about this case? Can you come up with a formula for p of t, or the population of lobsters, after some time t, such that it has a carrying capacity k? Whatever that is. Just say some k, some carrying capacity. Think about it. How would you derive an equation for this population? The curve will look something like this. Initially, it's going to grow exponentially, but then it's going to stop, right? Just think about it. What would you do to come up with an equation that describes this population? Future business majors? Devin? No? Nothing? Go ahead. Yeah. Detroit Lions, right? That's fine. I remember. Okay, so that's a formula. Do you think it's going to look like that? Or K minus P? Yeah, okay. Any other thoughts? And the answer could be, there's no way on earth I could find this equation. That's actually the right answer, unless you're like Chandrasekhar or some, math prodigy. This is a difficult problem. I ask you this question on purpose. because there is no obvious answer to it, because it is impossible in practice to find this actual curve, what it looks like that. The actual formula for this curve is this guy. P0k over P0 plus k minus P0 e to the minus RT. Pow! Like, there's no way you could come up with this formula out of the blue, right? That doesn't make, it's impossible. So that's the right answer. So how was this formula obtained? This is an actual formula, okay? I'll cite the reference in the next slide. This is an actual formula for populations of lobsters, okay? All right. So now let's take a different approach. My goal is to get to this formula, okay? And in the process of getting to this formula, I'll show you the power of differential equations. So let's take another approach, and instead of, the mistake we committed here is we were so empowered by the example of the paramecium. Oh, it's obvious, it's 2 to the power TP0, right? It's just like they're going to keep multiplying ad infinitum. Okay, we were so empowered to go directly after P. But my argument is going to be, no, let's not go after P. Let's go after dP by dt. Let's go after the rate of change of the population, because that is an easier problem to solve, as we will see. Okay, let's start with a warm-up. I want you to consider a population of lobsters with an initial size of P0. Okay, this is just a warm-up. Now that population, the birth and death rates for the lobsters is equal. Okay, so there's no change in this population. Now develop an equation that relates the rate of change of that population, so dP by dt, develop an equation for that. For a population of lobsters that doesn't change. What is dP by dt? P is the population. dP by dt equal? Okay, who says 1? Who says? I saw a lot of zeros. Yes, zeros. Okay, there's no change in the population. So dP by dt is indeed 0, which implies that P of t is a constant, as we expected, right? So equal birth, equal death and birth, okay? So dP by dt is 0. Okay, good. So in this case, we went after dP by dt, and from that we obtained P. That's going to be our trick. Okay, and it was easy to think about dP by dt here because we said there's no change in the population. Okay, all right, let's take it up a notch. Now, assume that the lobster population changes at some rate r. Okay, now this rate is going to be proportional. Is going to be a function also of the population itself, so that r times p lobsters are born every instant of time. Right? If you have p lobsters and they're changing at a rate r, so it's r times p lobsters that are changing over time. So now write the equation for dP by dt for a population of lobsters with a rate of change of r times p. What is that equation? I know there's going to be a little bit of a challenge to start thinking about rates of change now, but once you get over that barrier, it becomes easy. So RP new lobsters are added or removed per unit time. Now, so that's the rate of change of the lobsters, of the lobster population, right? So dP by dt on the left-hand side. Nothing? You got an answer? Okay, what is it? No, forget k. There's no k here. There's no k. So dP by dt equal rp, okay? Bearded dads. Same. dP by dt is rp. Why? Because the rate of change of the population is r times p. I kind of said that up in the statement. Indeed. Yeah. dP by the rate of change of the population is equal to that growth rate times the population itself. Okay? So again, we went after dP by dt. And in this case, that rate of change of the population is equal to this growth rate times the population itself. Okay? That's a differential equation, right? You've done that. You've seen that differential equation, hopefully in high school, maybe in your ODE class. And guess what? The solution to that one is nothing more than that formula that we developed kind of by recursion, right? P0 e to the RT. Now this is powerful. Again, we went after dp by dt, and from that, we obtained a formula for P. Okay? All right. So now, to the elephant or the lobster in the room. Okay? Now, what if the population cannot sustain more than a certain percentage? Like I said, that carrying capacity K. Develop a differential equation for a population that has a carrying capacity K. And here's the tip. By now, I hope you recognize that the right-hand side of that dp by dt is so important. It tells the rate of change what it's going to do. If it's 0, it's going to stay flat. If it's positive, it's going to go up. If it's negative, it's going to go down. Right? In this case, we kind of want to switch on the right-hand side so that when p equals to k, the entire right-hand side becomes 0. So what is that right-hand side? What? Think about it. Give it some thought. You want to switch on that right-hand side. Look at that last statement I have here. Instead of having r as your growth rate, you want r times something minus p. Now that something, when p is equal to k, that becomes 0. Times k minus p. Max? K minus p. Root, rascals? K minus p. Anybody against k minus p? Anybody opposed to k minus p? Okay, this is not a democracy. There's one answer. Okay, so, but I'd like to discuss it. So, okay. Well, that's right. That's the right answer. Okay. So instead of having this r times p, where you have unfettered growth or decline in a population, instead of this r, standard growth rate, what if we put r times k minus p? So that when p is equal to k, that becomes 0, right? So you've knocked out that growth rate. And then you put that in your equation. Look at that. That's a fairly complex differential equation. It's a nonlinear one, okay? And now you look at that. I want you to think, before we see the answer to this differential equation, what happens, remember what I always tell you, look at the extremes. What happens when p is very small, in this k minus p, or when p is equal to k, on those two extremes? Initially, when the population is small compared to k, you're starting, okay, so let's say k is 100 lobsters or 1,000 lobsters. Initially, you're starting with 2 lobsters. 1,000 minus 2, right, is a very large number. Okay? So it really doesn't affect that population growth. But as p approaches 1,000, say 999, right, or 1,000, that number becomes 0. And the entire right-hand side becomes 0. What happens when the right-hand side becomes 0? You go flat, right? And indeed, the answer to that differential equation is nothing more than that formula I gave you earlier. So nobody developed that formula just by thinking about it. Again, maybe some math prodigies would figure that out. But us normal, average people, right? We have to go by they're very powerful, right? They equalize the playing field differential equations, right? They allow us to come up with formulas like this one. Okay? Okay. And this is how the formula was derived. And actually, you can find this in a Nature article, how populations grow and the exponential and logistic equations. Okay? Okay. So here are some philosophical definitions. In general, it's easier to relate rates of change. I know you might have found it a little bit challenging, but that challenge is because this process, this thought process is only new to your mind. But that's what we're here for. Once you go through this process a few times, becomes a piece of cake to come up with these differential equations. You relate rates of change instead of the thing itself, right? It's far easier. As you get to your junior courses with heat transfer, mass transfer, kinetics, you will find this incredibly useful, this thought. Here's one of the best statements I like to think about differential equations. The solution to a formula is a number. The answer to a formula is a number. The answer to a differential equation is a formula. Think about that. We have elevated our abstraction of how we describe physics and physical laws, right? The answer to a formula is just a number. The answer to a differential equation is a formula. That is very powerful. And if you're curious, you might ask, well, a differential equation is the answer to what? Okay? If you've ever heard the word calculus of variations or variational principles, that's an even higher level mathematical abstraction that helps you generate differential equations. But that's beyond this course, okay? Now, the formula that results from the solution to a differential equation is usually used as an algebraic relation that you use to generate numbers, etc. Okay? All right. So now I want you to think of some examples from your daily life where I want you to think differently about something you do every day and think of it in terms of a rate of change. Okay? Like the rate of change of the food in your fridge, right, by the end of the week, right, versus the rate of consumption, the rate of change of your savings, as you go out and dine and eat, etc., right, and buy books and guitars, things like that. So go ahead, list a couple. I'll have Mr. Larry back. I love it. I see everyone's hands doing this and that. I love it. All right, bearded dad, something about kids, my guess, like the rate of change of milk in the fridge or or how many diapers. Energy. Oh, yes. Uh-huh. Okay, that's right. Business majors. Okay. Elizabeth? The rate of change of the water in your mug?
I'm going through like a middle crisis too, so I just bought a bike, and so
Oh, okay.
so much.
What kind of bike? Love it. Okay, yeah. Numerical ninjas, anything? Walking? Okay, yeah, your pace, right, as you're walking. dx by dt, right? So position. All right. 2648719. Yeah. And that correlation to that? You guys have an answer? I saw you doing with the hands, Sarah. How it changes throughout the day? Yeah. All right. Floating point falcons. Okay, yeah, exactly, yep. How your car consumption and, with traffic. Detroit. Mm-hmm. Okay, they're all rates of change. Rowan.
Rate of change of serotonin when I eat pizza.
You always have these interesting stories. Love it. All right, you guys.
We said the rate of change of the radius of the pancake.
Of the radius of the pancake as it's.
As I pour it on a griddle.
Oh, okay, okay. That's interesting. Thinking technically about cooking. Do you have any thoughts?
You said likelihood of quitting your job before payday.
And then runs.
You said sleep throughout your life.
Sleep. Oh, as you sleep less. You get, yeah, that's a good one. Bernoulli. Oh my God, I was thinking about that. Like, what I would do is like when my hair started falling out. Believe it. Of the major, yeah, exactly. Through my PhD, that's when it all happened during my PhD. Like beginning, I had like dreadlocks. By the end, I was all shaved. All right, love it. Okay, yeah, I put some examples here, like rates of change of population, your position, velocity, acceleration, etc. During the pandemic, when we had rates of infections and death and things like that. Rate of interest on your loan, growth of your investments, or water. All right, so we'll start digging into differential equations now, get into the technical jargon and what's going on behind the scenes. In general, we distinguish between ordinary and extraordinary or partial differential equations, okay? So we will start studying ordinary differential equations. For the most part in this course. We'll do PDEs a little bit at the end. But in ordinary differential equations, it just means that it has ordinary derivatives. So by definition, what that means, when you have an ordinary derivative, that's for functions with a single independent variable. So by definition, an ODE is one-dimensional in that sense. You only have either space or time or whatever other variable you're thinking about. Okay. So it can only contain ordinary derivatives, a population growth equation like the one we saw earlier, the rate of change of height in a tank where you're filling it and it has a hole in it, for example, like a hole in the bucket, right? So this would be the equation. Torricelli's law is derived from that equation. A advection diffusion equation is also an ordinary differential equation, 1D, rate of change of concentration, for example. Those are all examples of an ordinary differential equations. The telltale sign is when you see a ordinary derivative, okay, the symbol D, okay? Now, a partial differential equations is more complicated. It has partial derivatives, which by definition means you're dealing with a function of two or more independent variables, and your derivatives can go over all of those variables and combinations thereof. So really unlimited complexity when you go into higher dimensional space. So a diffusion equation or Poisson Laplace equation in 2 dimensions, unsteady heat equation, for example, combining time and space. So T is time, X is space, X and Y are space. You've seen some of this earlier in the course as well. Unsteady advection diffusion equation. So for example, when you look at this equation and this equation, once you drop the time term, you become an ODE. But over here with time, you can also change in space. So that adds more complexity to it. Okay, we're going to talk about ODEs for now. So we will forget about the right column here. We're going to talk about only the left column, ordinary differential equations. Now, with ordinary differential equations, we have another classification, okay? And that classification is into 2 categories, initial value and boundary value problems, or in other words, propagation problems or equilibrium problems, okay? An initial value problem is a problem where you know the state of the system at some initial time, and you say, go. What happens? Okay, I know the initial population of lobsters. Go. What happens? Okay, I know the initial concentration in a pot. I'm adding heat to it or adding some reactants to it. Go. What happens? Okay? So that's an initial value problem. It only depends on the state of the system at some time, that initial time. So in other words, this is an initial condition, and what's happening next? Okay, what happens next? They're kind of nice that way because when you think about time, you're like moving in that one direction only. Classic problems are changes in concentration. You'll see this in your junior year next year. Rate of change, again, Torricelli's law, rate of change of the height of a water column in a bucket. There's some hole in it, so you're draining some water, but you're filling it. So that height changes over time according to this equation. So it's only the initial condition that matters. So in that first problem, the initial concentration is what matters in that tank. Over here, the initial height of the water is what matters in that system. Clearly, what you're bringing in and what you're taking out, but those are not boundary conditions. They're just system conditions that constrain the evolution of the system over time, but they are not boundary conditions, okay? And other things, population growth, pandemic, disease spread, we're going to develop a pandemic model together for COVID, for example, and how it was spread, et cetera. And that is only going to be an initial condition problem. Now, boundary value problems, you are given the state of the system on the boundaries. Okay, so again, this coffee mug or the wall, the temperature on the outside and the temperature on the inside. Remember the rod, the heat transfer on the rod that we studied early on when we're doing systems of linear equations? We fixed the temperatures on both ends, and we asked the rod, what's happening to the temperature in between? So that's a boundary value problem. Okay, the initial temperature of the rod is insignificant in that case because we're looking at the final state on the system given those two boundary conditions. All right, so that was one of the problems we solved early on, but now we're going to understand where it comes from. And again, I'm not going to teach you how to derive a heat transfer equation. You're not responsible for that. You'll learn that in heat transfer. But I'm going to give you the tools to understand, and when you see that equation, to understand how to solve it and understand what it means, okay? I'll try to add as much physics as I can given, the knowledge that you've accumulated so far in your learning journey. All right, so spring mass systems, constrained beams, and their curvature, what matters are only the boundary conditions. So you set the state on the boundary and see what happens inside the system, okay? So then by definition, an initial value problem requires one or more initial conditions. If you have many equations, you require as many initial conditions as there are equations. And for a boundary value problem, you require boundary conditions, okay, on both ends of the problem. All right. Now there's more classification. A first order ODE contains only first derivatives of the dependent variable. So d phi by dt is equals some right-hand side of t and phi, okay? So from now on, for initial value problems, I'm going to use t as the independent variable to designate time. Could be any other symbol, it's just a symbol. But to simplify our communication, I'll just use t. And when you see t, you think, oh yeah, this is a time-dependent problem. It's most likely an initial value problem, okay? So a first order ODE is an ODE that has at most a first derivative in it, okay? At most a first derivative. So you could have a function of time or a function of space. Okay, it doesn't matter, just a symbol. You can also have systems of equations of ODEs. We write those as a vector. Okay, so if you had phi1, phi2, phi3, phi, and so temperature, pressure, velocity, energy, concentration, all of those, put them in a vector. Each one of those has an ODE of its own. You just put them in as a vector, and you'll have a vector of right-hand sides for each ODE. For each one of those dependent variables, you have a different right-hand side. Okay, we'll come back to that system of equations nomenclature later. A second order ODE contains second and possibly first derivatives and so on. And kind of that's the order. A third order ODE is going to have third derivatives and so on, right? We're not going to get to third order. We'll only do first and second order ODEs this year, okay? So the advection diffusion equation, this is a very popular equation in chemical engineering. You will hear about it a lot. It's two different processes happening physically at the molecular level and at the macroscopic scale. So, I don't know if you've been to our department. Sometimes you come in and you hear this delicious smell of cookies. one of the people at the front desk, apparently they always make cookie, or it turns out they have like a incense thing, the burner thing that makes the smell of cookies. It's very delicious, but why do you smell it? Like suppose I had an incense stick over here and I burn it, right? And that incense, that smoke, if I like put a fan on it, right, it's gonna blow, it's gonna take that smell, whatever material that is, it's gonna bring it to your nostril and you're gonna smell it, right? So that process is called advection, okay? That process is called advection. So that's what you see on the right-hand side on the second term over here. Again, you're not responsible for this, but I want to at least expose you to some of those words. So this is a very popular process in chemical engineering. Diffusion occurs at the molecular level where these molecules are always kind of shaking and moving and transmitting information, right? You put a drop of ink in water and you kind of see it diffuse very, very softly. So that's diffusion. If you remember good old cartoons, you know, bake a pie and you smell that, right? So there's diffusion and advection, right? So if you have an apple pie here, a change in apple pie smell. You have some wind blowing and you're standing here, oh, you know, you smell it and you're gonna be attracted to the pie. Actually, a lot of creatures, us included, we rely on our sense of smell to determine direction, right? So, which essentially our brain is kind of solving an inverse ODE problem, trying to figure out where is that smell coming from. Okay. An example system of ODEs, so I talked about systems of ODEs. Here's an example that we're going to do together, is a system to model a pandemic such as the COVID-19. So I put those slides together when we were hit with COVID-19. So there's like a model out there, and together we developed a more complicated model. So we will come to this together, and I'll show you how you can actually derive it by yourselves. But this is an example of a system of 3 ordinary differential equations that track people who are susceptible for the infection. That's the variable S. People who are infected, that's the variable I. And people who have recovered, that's the variable R. And if you solve this system with some parameters for these coefficients, whatever they are, you get something like this. Initially, most people is susceptible, and you might have like one infected person. So susceptible is blue, red is infected, and green is recovered, okay? So if you have one infected person, right, they interact with the susceptible people. Then, as the susceptible people get infected, right, they're going to shrink, and they're going to move from being susceptible to being infected. But also, some of the infected have recovered after, 14 days, right? So they've recovered, they turn to green, and then by the end, everybody is recovered. Okay? So with differential equations, you can model something as complicated as a pandemic. And believe it or not, epidemiologists, they use still this simple model. They add to it a couple of equations. You could add, for example, hospitalized, deceased, vaccinated, etc., masked, unmasked, all of those things. But all they care about is those parameters, beta and nu and whatever. Once they found those parameters, they fine-tune this model, and they can make predictions. It's just as simple as a system of ordinary differential equations. Okay? There's another setup. This slide doesn't belong here, so I'll come to it later. Okay. Another way to get to systems of ODEs, which is order reduction. We're not going to cover that right now. Now I'll ask the question, why do we use numerical methods to solve ODEs? Well, kind of obviously, there's not always an analytical solution, right? I wish there were. Only in simplified cases there are analytical solutions. But most cases, these equations are coupled nonlinear. They're very nasty, very annoying to deal with, very complicated. So our best bet is to go and solve them numerically. Okay? Let's resume, please. We're going to start digging into initial value problems. So we will spend 3 to 4 lectures perhaps on initial value problems. We'll solve them in Python, learn the tools in Python, and then we'll dig under the hood of what Python is doing. Okay? And now comes the story of the lobster. We are going to cook a lobster together in Python. If you're vegetarian, substitute the lobster with a vegetable of your preference, like a zucchini or eggplant, right? And this explains the statement here on the shirt, like lobsters, the original test subjects for heat equations. Okay, we're going to solve the heat equation on a lobster together in Python, okay? So apparently, a and this is completely satirical. Please don't fact check this slide, okay? A recent report found that the population of lobsters is growing out of hand, and that those lobsters are eating everything at the ocean floor, like disrupting the global ecosystem, causing climate change. They're like eating everything, each other, they're eating the sand, they're eating everything. They're eating sharks, okay? And then, the WHO and CDC and like the world leaders, they came together and they're like, okay, we need to stop this. We need to stop these lobsters. And they started recommending that people start eating lobsters as snacks. Like you go just like eat them as snacks, like you're walking, eating lobsters, and you go buy a bag of lobsters from Starbucks in the morning with your latte, okay? So just to help control the population. But they wanted to hire you as an engineer. Now these different companies, they realize, okay, it's open season on lobsters, we're gonna go hunt all the lobsters, but they tasked you as an engineer to figure out the fastest way, okay, to cook a lobster. Because, you have a client in the morning coming in 6 in the morning. Hey, can I have 17 lobsters, as baguettes, like together in a bag? And so and you have two options. You could either boil it in a liquid, like water or oil. You have to figure out, what that liquid is, okay? Or bake it in the oven in a different environment. And you understand, with liquid, you have a different mechanism of passing heat to the lobster. You boil the liquid gets hot, and as the liquid gets hot, it passes that heat to the lobster, okay, and the lobster gets cooked. Whereas in the oven, there's no liquid, there's just air, but the medium of heating is radiation from the coils, okay, or even if you have a convective oven, most they say is just coils through radiation, you're cooking the lobster, okay? There's apparently Maine lobsters are apparently very popular. So there's a true story. This is a true story. As I was putting these slides together, I read this story in Maine. There's a very famous restaurant. Apparently, they infuse the lobsters before they cook them. They want to cook them humanely, and so they give them weed or something. They like expose them to like weed smell so that they're like kind of more relaxed. And apparently they taste better if they're more relaxed. Anyway, it gets really weird. So anyway, that's as far as we're gonna go with lobsters. They're just pictures on the slide. Okay, we're gonna treat them as, just to do the heat equation. Okay. There are also other reasons I choose lobster. There's historical precedent in this course, but anyway, we're going to keep the lobsters going on. That's why you've been seeing a lot of lobsters in the ICC room. We've been printing all of this gear and merchandise for the lobster, so they're getting very popular. Okay, now the assumptions. We're going to assume that the lobster is a cylinder. Hey, it's not that bad. A lobster, seriously, you grab the lobster. Oh man, I should have put the picture of when my son had his first lobster. It was like almost his size. We went to Red Lobster, and he loves seafood, and so. But really, the tail of the lobster, that's kind of the one of the best parts, right? It's like a cylinder, right? It's not a bad assumption, okay? It's not as bad as assuming a chicken is a sphere, right? Like in physics. Anyway, so the lobster is a cylinder of length r and radius r. Of length L and radius R. Again, I'm not asking you to derive this. I'm just showing you the process, right? Just kind of these parameters, and I will give you the equation. I am going to give you the equation. In your junior year, you will learn more about how that equation came about, okay? And the lobster remains at a uniform temperature throughout the cooking. Why? Because I want it to be only a function of time. If I allowed the lobster to change temperature from head to tail, there's going to be a gradient in space. So I will have change in time and space that becomes a partial differential equation. No, I don't want a PDE, I want an ODE. And it's a very valid assumption. The entire lobster is dipped in that same sink or source of heat, right? So all of it is going to be at the same temperature. And it's kind of very thin as well. So it's a good assumption. The lobster doesn't lose mass with time, and the heat capacity, that's the ability of kind of how much a unit of mass in the lobster is changing heat, is increasing its temperature, right, as you change the temperature of the surroundings, right? So how much energy that lobster can contain as you heat it up. It's that of water. because it's mostly made of water, right? So, and it's not that bad. For water, it's 4,200. For lobster meat is about 3,800. So we're just going to use the number from water, for water. So we have L, 30 centimeters, and radius of 10 centimeters. The surface area of the lobster is what matters. So for this cylinder, so you got the area of the front and the back of the cylinder, and the surface area of the cylinder itself. So we get that area 2 pi RL plus 2 pi R squared. And the mass is 1 kilogram, and that heat capacity or specific heat is 4,200. Okay? Now, indeed, when I went on dimensions.com, and apparently they have the dimensions of a lobster. Like, can you imagine? Lobsters are popular for some reason, right? And so they have the dimensions of the lobster, and my numbers are not off. So, in general, you get 20 to 60 centimeters. We picked 30 centimeters. And for the width of the lobster, that's kind of the diameter. They had 5 to 15 centimeters. So, we picked a radius of 10 centimeters. That's not entirely wrong. Okay. All right. So with these numbers, there's two processes. And again, I'm just going to give you the differential equations. I'll explain to you what the terms mean. All right. But you will learn more about them in your heat transfer course. But here we want to learn how to solve them. So when you boil it in a liquid, this is a process called convective heat transfer. And it comes from the word convection, where it's a motion with a fluid. It could be a gas or a liquid. Okay? Convection is a process where a fluid is moving information around. All right? So in this case, the fluid is water or oil or an air fryer, let's say. It's moving heat through the fluid itself, right? So the fluid is moving the heat. That's the kind of information that you're passing to the lobster. Okay, and the equation is rate of change of temperature of the lobster. Don't say derivative anymore. Say rate of change of the temperature of the lobster. Use words. Math, they used to write words to describe math equations, not symbols, right? So try to use words so you understand what you mean by this equation. The rate of change of the temperature of the lobster with time is equal to some coefficient. There's a negative sign here, but it's equal to some coefficient. We'll talk about that in a second. Times T minus T infinity. Okay, so T is the same temperature of the lobster. T infinity is the surrounding temperature of the fluid. So water boils at 95 degrees in Sandy, or here kind of in Salt Lake, 97 degrees. That's T infinity, right? Now think about the carrying capacity. What happens when the lobster temperature becomes equal to the temperature of the liquid? This term goes to 0, so there's no more change. So with boiling in a liquid, in oil or water, that lobster is going to hit a fixed temperature, which is going to be equal to the temperature of the boiling liquid, and it's going to stay there, okay, until the liquid evaporates. Now the coefficients, there's the area of the lobster, that's A up there. There's the mass of the lobster, the specific heat, how much its heat capacity, how much it can contain. H, if you remember our heat transfer in a rod example, you kind of saw this equation earlier when we were cooling or heating a rod, if you remember. Now it comes again to us. Now that H is how effective the liquid is in passing its heat content to the lobster. The higher the H, the more effective the fluid is in passing its temperature or its heat content to the lobster. So that's why you might choose oil, because oil has a higher H value. H is called the convective heat transfer coefficient. Again, we heard that before early in the course. You hear it now. But from your perspective now, this is just a coefficient. H is going to help you determine what fluid you want to use, right? So you might say, okay, I'm going to try water, then we're going to try oil, or we're going to try some other synthetic fluid that has very high H. And you say, okay, if we want to cook the lobster in 5 minutes in this liquid, we need a liquid with a heat transfer coefficient of 1,500, for example, joules, whatever units, meters squared second, etc. Okay? Now, when you bake it in the oven, you still have a rate of change of the temperature of the lobster with time. You have a bunch of terms here, area, etc. Forget those for a second. But then you have this T to the power 4 minus T infinity to the power 4. So it looks like that one, but it's raised, each term is raised to the power 4 because radiation is a very highly nonlinear process. And it's just so works passing heat as the fourth power of the temperature. T infinity is the ambient temperature on the oven. And that could be if you're broiling it at 550 Fahrenheit, or you're baking it at 425, for example, right? That would be your T infinity. But raised to the power 4, okay? So look at how much it amplifies it. And T is the temperature of the lobster, T to the 4. Boltzmann constant sigma is a very small number, so it kind of tends to reduce the amplification effect from the power here. A is the area, M, Cp, or mass, and heat capacity for the lobster. Epsilon has to do with like black body radiation, how transparent the medium is. We're going to set epsilon equal 1 to assume we have perfect radiation transmission in the oven. Okay, you could put 0.5 or 0.75. It's not going to make a very big difference. Okay, we'll see. Okay, so now these are our two equations. They are differential equations. There are exact solutions to those. I'm not going to show those because we're going to hit it numerically. Okay, we're going to assume like, yeah, this is just too complicated to think about analytically. We're going to solve it numerically. This is a numerical methods course. So what is the strategy to solve an ODE? We'll talk about the strategy, how we do it in Python, and then next lecture we'll derive by hand. Okay? So in general, to solve a general ODE, I'm going to write them in this form. d phi by dt. Phi is your dummy quantity as we've agreed on since the beginning of time, of the semester. Phi is a dummy quantity, temperature, pressure, density, velocity, whatever you want, concentration, is equal to some right-hand side. So this right-hand side could be your convection boiling right-hand side minus some coefficient T minus T infinity, or your radiation right-hand side. It's some arbitrary right-hand side. With an initial condition, phi 0, so that's the initial temperature of the lobster in this case, right? And we're going to run it from some initial time to, let's say, 10 minutes. See how the temperature, if we're boiling the lobster for 10 minutes, what its temperature going to be after 2 minutes, 3 minutes, 4 minutes, 10 minutes, and so on. Okay? What we will do, this is with after this red curve, right? The change in temperature over time. We're going to divide the time space or the time segment into smaller chunks, like we did when we solved the heat transfer in the rod problem, if you remember. We're going to do this over time instead of space. Okay? You can make those intervals equal. You can make them not equal. It doesn't matter. We can find solutions for in either case. For simplicity, let's assume that the size of the interval is equal on that time. You say, I want to divide my time interval into 100 time steps. We call those steps, right? Like we said with the grid earlier. And then your objective would be to develop a formula somehow to find all of those values for phi, or the temperature, at each of those times. Remember, we can't solve this continuously. That's not an analytical solution. This is a numerical solution. So we predetermine the times at which we want to find our answer. And then we have to develop a formula that we use from the initial condition all the way forward to find all of those discrete values. Okay? We will start with Python. And I'm not sure we're going to be able to do all of this today, but let's at least introduce the routine. So we'll start with Python. So we'll teach you how to drive first, and then we dig under the hood. Okay. SciPy comes to the rescue. So SciPy.integrate, big module, has a library for solving ODEs called ODE-int. Okay, there's another one called solve IVP, but that's kind of a bigger can of worms. So we'll look at ODE-int. And if you're doing MATLAB, that's consistent with MATLAB as well. There's ODE 45 in MATLAB. So ODE-int for ODE integrate. Why? Because we're integrating these differential equations. We're integrating the derivatives, right, to find the dependent variable. ODE-int solves an ODE of the form generically. Any ODE, you can give it any ODE, specifically an initial value problem. It solves it of the form d phi by dt equals some right-hand side of phi and t. Now be careful here. I want to stress this in a minute, that the arguments for the right-hand side need to be in that order. Phi, comma t, not t, comma phi. Okay, so that's very important. As we've seen this on numerous occasions with Python, they predetermine kind of what the right-hand side, what the form of the routine needs, what the argument order is. Okay. ODE int takes this form. You call ODE int, you give it a right-hand side. These are the least, this is the least number of entries you need in ODE int to solve an ordinary differential equation. Okay? It takes a right-hand side, phi 0 and t. Let's see what those are. RHS is simply the name of a Python routine that you wrote to describe the right-hand side of your initial value problem. So think about the lobster. We're going to write two right-hand sides. One right-hand side convection, or boiling it in a liquid, and another one for radiation. Okay? What do you give it here? So let's say you call the right-hand side convection, cooking Mr. Lobster with convection. That would be the name. That's what you would put here. Python internally, automatically, is smart, figures out, oh yeah, I'm going to call that. That must be a Python routine. I'm going to go find it in the code, and I'm going to call it. And I'm going to pass some parameters to it, and I'll do my thing. Okay? Works magically. Remember fsolve, when we gave it the name of the residual function. It was a simple Python routine. We passed the name of the residual function. Okay, and it figures that out. Same thing here. Now be careful. You have to define your right-hand side in this order. Phi, comma, t. Not t, comma, phi. The first argument in your right-hand side routine in Python needs to always be that dependent variable. Okay? Whatever you call it, phi, q, whatever, Python figures that out. That argument here needs to mean the dependent variable. This argument here means this one means the dependent variable. This one means the independent variable. Okay? In that order. Phi 0 is your initial condition. It'll be just a number. Okay? It's just a number. This is a single ODE. T is an array, a sequence of times. Guess what? We've done that numerous times with linspace. Okay? You take an interval, you divide it into equally spaced points. They don't have to be equally spaced. You can do a log space, or you can manually put them in, or read them from a file, or somehow generate these different times. But the point is that ODE int is going to solve your ODE at those times that you provide. 0, 0.1, 0.7, 0.71, 0.8, 0.9, etc. It will make sure it gives you a value and answer at each one of those points. Okay? And finally, ODE returns an array that contains the answers at all of those times. Phi at t0, phi at t1, and so on. Okay? So I only have like 3 minutes. We'll do the coding activity together on Thursday, because I don't want to interrupt it. So on Thursday, before you leave, please, on Thursday, we'll pick up from here. We'll review ODE int, and then we'll go to our Jupyter notebooks, and we'll together start building the right-hand side. We will build a right-hand side for boiling it in a liquid, and a right-hand side for baking it in the oven. And we run each one of those in ODE int, and start changing parameters. What happens when you change h over here? What happens when you change t infinity? What happens when you change t infinity here, like you're broiling it or you're baking it, right? What happens when you change the emissivity, etc. Okay? Thank you so much.